Going on, Algebros? It's Mr. C, and in this video, I'm going to share with you some secrets of graphs of basic log functions. Alright, so I'm going to give you some general properties of log functions that have this format. F of x equals log sub a of x. So keep in mind that a represents the base of the log, and it's actually the base that you're going to analyze in order to get started with these sketches. So let's take a look at when the base is larger than 1. So this would include log functions such as log base 10 of x, which is the common log, or simply log of x. It would also include log functions such as the natural log of x, which is log base e of x, as well as something like log base 2 of x, and you can imagine that there are many other logs that would fall in this category. So um, regardless of the base's number, as long as it's greater than 1, here's what you can expect the graphs to do prior to any transformations. So each graph will go through the point 1 comma 0, and to the right of this point you'll have an end of the graph that slowly increases to positive infinity. To the left of this point you'll have an end that curls down towards the y-axis and heads down to negative infinity. Now, it's never going to cross or intersect the y-axis. So what that means is that the y-axis will serve as a vertical asymptote. So we have one end, the right end, slowly creeping its way up to positive infinity, and the left end curling towards the y-axis, heading down towards negative infinity. And it will go through the point 1 comma 0. Another point that it will go through is a comma 1, where a represents the base of the log function. Now the domain of the log function prior to transformations would be parentheses 0 comma infinity, and the range would be all real numbers. And I want you to notice that this is actually the reverse of the domain and range of the exponential function. And hopefully that makes sense because logs are inverses of exponential functions. Moving forward, the graph will increase as you go from left to right, and it contains the points 1 comma 0 and a comma 1, and has a vertical asymptote equation of x equals 0, which that's the equation for the y-axis. So there's information on how graphs of log functions will look when their base is larger than 1 and there are no transformations. Let's take a look at log functions where the base is less than 1. So these would include log functions such as log base 1/2 of x, log base 0.3 of x, or log base 3/4 of x. And just like there are many of the log functions where the base is greater than 1, there are many log functions where the base is less than 1. So for these sorts of log graphs, they will still go through the point 1 comma 0. But to the right of this point, we're going to have an end that slowly decreases towards negative infinity. To the left of this point, we'll have the other end curl up towards the positive part of the y-axis without ever crossing or touching it. And that would qualify the y-axis as another vertical asymptote. So we have the right end this time heading down to negative infinity very slowly, whereas the left end curls up towards the y-axis heading towards positive infinity. A comma 1 is also on this graph, but it's going to be to the left of the point 1 comma 0. Now, like we saw with exponential functions, all of the characteristics of this type of log function graph will be the same as the previous ones. So that would mean that the domain is from 0 to infinity. The range is all real numbers. This time it decreases from left to right. That's the only difference. Contains the points 1 comma 0 and a comma 1, and has a vertical asymptote of x equals 0, which is the y-axis in disguise. Alright, so that's it for this video. As always, let me know if you have any questions regarding the content in it. Otherwise, thanks for watching, and I'll see you guys in the next one.